Area between two curves. The area of the hexagon is 127 square units. The area of the circle is 39 square units. What is the area of the green shaded region? Calculating the area of obscure shapes involves either adding or subtracting multiple areas of polygons or shapes that you have here. In our case, since the shaded region is outside of the circle but inside of the hexagon, we have to subtract. So we're going to take the area of the hexagon, 127 square units, and subtract from it the area of the circle, 39 square units, to get an area of 88 square units. The next application of integrals that we will encounter is calculating the area between two curves. Previously, we have only used integrals to calculate the area under a curve that was bound by an axis, as shown in the graph below. But what about this situation? How would the area, shaded here, that's bound by two different functions be calculated? We could find the area below the curved section, as shown here, shaded with purple, and then we could subtract out the area bounded by, in this case, a linear function. And then the resulting area will give us the shaded region. So we're going to subtract the area below the bottom curve from the area below the top curve. A definite integral will be useful here when calculating these areas, but what values would be chosen for the lower and upper bounds? If the points of intersection are not given to us or clearly marked on a graph, then they can quickly be calculated. So you can find the bounds of integration by calculating the x values of the intersection points of the two functions. So if we were to actually take y equals x and 3x minus x squared and set them equal to one another and solve for x, we can determine those bounds. So we would have that 0 is equal to 2x minus x squared, and we can factor in x out of both terms, so we have 2 minus x. So x would be 0 and x would be 2. In this scenario, we can also visibly see that the area starts at x equals 0 and then goes until x is equal to 2, which are the two solutions that we found out algebraically on the previous slide. So those are going to be our bounds of integration. Recall from the warm-up about the area of the hexagon and circle. To calculate that shaded region, we subtracted the area of the missing shape from the area of the larger shape. And the same idea applies to this situation when writing the integral. We have the integral from 0 to 2 of the outer region, which is 3x minus x squared, minus the inner region, which is x. And we're going to integrate and evaluate with respect to x. In general, we have arrived at the formula for calculating the area between two curves. That area is going to be the integral from x of 1 to x of 2 of the upper curve minus the lower curve with respect to x. Now let's try to find the area that's bound by these two curves. We have y equals x and y is equal to 3x minus x squared. Let's get started. The first step is to set up our general formula with 0 and 2, the x coordinates of our points of intersection, as the lower and upper bounds of integration. So we're going to do the integral from x of 1 to x of 2 of the upper curve minus lower curve. So that will be the integral from 0 to 2 of 3x minus x squared minus x. And we're going to integrate with respect to x. And next we're going to integrate and evaluate. And this is pretty straightforward because we're using the power rule here. So we're going to have 3/2 times x squared minus 1/3 x cubed minus 1/2 x squared. And we're going to evaluate that from 0 to 2. So if we substitute 2 in for each of these x values, we'll have 3/2 times 2 squared minus 1/3 times 2 to the third minus 1/2 times 2 squared. And then from that, we're going to subtract this expression evaluated at 0, which is minus 0. So now if we evaluate this, we have 2 squared is 4, 4 times 3/2 is 6, minus 2 to the third is 8, so we have 8/3, minus 2 squared is 4, and half of that is 2. So then we'll end up having 6 minus 2, which is 4, or 12/3, minus 8/3, and 12/3 minus 8/3 is 4/3.